voltage across the inductor is, like I said, is going to be in opposition, sort of like that's our induced EMF. It's going to start out high because it's freaking out, and then it's going to relax over time until it's not there any longer. And so its max is the EMF, yeah, the EMF of the battery.
And what is this graph of?
This is voltage across the inductor as a function of time. And this is current across the inductor as a function of time. And then our last equation is the voltage across the resistor. And since they have to sum up to be the battery voltage, then since the inductor voltage starts out high and goes low, then the resistor voltage is going to start out low and go high, so that they always sum up to equal the EMF of the battery. Actually, those are two plots I could put on the same graph since they've got the same units. And then you can really see that they're always in opposition to each other. Okay, so that's the rising case. Any questions about RL circuits so far? Now for the falling current, and I probably should have said this before, but this is a special kind of switch. It's called a make before you break switch. And you have to make the connection at B before you break the connection at A. Otherwise, if you moved it away from A, at that instant you'd go from current to zero current, which if you did that is going to freak out your inductor. It's going to create a huge spike in magnetic field and could cause problems. So you have to make the connection at B before you release the connection at A. So once we're in the falling current state, you're not connected to the battery anymore. And so the current is flowing from the battery and it's sort of petering off. So your current is decreasing through the inductor. The inductor wants to keep everything the same. So now it drives the induced EMF in the same direction. So unlike the RC circuit, for the discharging case, the RC circuit, the current switch directions. For the falling current case, the RL circuit, it's going in the same direction as it was before. So your current is going to be whatever the current was before you switched it, that's I naught, and then it's going to peter off till zero as it burns up through the resistor. And then we can evaluate the voltage drops as well. And just like the RC circuit, everything is going to zero this time. Except there has to be equal and opposite signs on the inductor voltage and the battery voltage. And so this is based on the induced EMF equation, how it had the negative sign in here. So now we can kind of use that to our advantage and say, since the induced EMF switched directions from the rising to the falling case, then we can apply a sign. Oh, don't turn off. We can apply a sign difference to the voltage drop across the inductor versus the voltage drop across the resistor, so that they'll always sum up to be. Let's see. They're not going to sum up to be the battery voltage. No, because they're not connected to the battery anymore. I naught times R. Well, I guess the battery voltage was EMF over R. that's interesting. I guess what you could get at the very beginning is that the sum of the two voltages, oh no, the sum of the two would always be 0, which makes sense because it's not connected to a battery. Okay, I apologize as I'm trying to figure out this stuff as well. So because these equations are added together to be the total voltage across the circuit, that's why I was kind of like trying to figure out what they added up to, but obviously they'd add up to 0 at every point in time. So this is I naught R plus I naught R, and this initial value would be minus I naught R. Okay. All right, so that's the falling current case. So we've got 6 new equations and new behaviors for this RL circuit. So any questions before we try out our examples? No? Okay. I hope you wrote the equations down. If people didn't, I guess I can write them on the board. All right, so problem 30.27. We have a figure showing an RL circuit, and we're given the EMF, the resistance, the inductance. When switch 2 is open and S1 is closed until a constant current, switch 2 is open and S1 is closed until a constant current is established, then S2 is closed and S1 is opened, taking the battery out of the circuit. So, given the setup, what are we dealing with? Rising current or falling current?
At what point in time?
After the description. So after these events have happened?
Falling current if the battery is taken out?
Yeah. So after they've opened S1 and closed S2, then the battery is no longer part of the circuit, so we'd have falling current. So at time equals 0, what is the initial current in the resistor? So we're talking about falling current. What would the initial current in the resistor be?
60 volts over 240 ohms.
Okay, so you're just taking the EMF of the battery divided by the resistance?
Yes, because at steady state, the inductor is a short circuit.
Yeah.
Because it's a DC.
Yeah, so right before it closed, it was feeling all the voltage of the battery. It was a steady state current, so that's just V equals IR, I equals V over R. Yeah, and so it wouldn't matter whether you're talking about the inductor current or you're talking about the resistor current. They're in series. They feel the same current. B, what is the current in the resistor at time equals 4 times 10 to the negative 4 seconds? All right, so that's when you guys can calculate. And then C, what is the potential difference between points B and C at that time? Okay. So I guess it looks like questions B, C, and D are just ones you have to work out with equations, not concept questions. So I guess spend some time with these equations, see if you can figure them out. I'll answer them on the board if people are getting stumped.